Okay, first of all, I'd like to thank the forum committee for okay, there we go. First of all, I'd like to thank the forum committee for inviting me to give a talk today. Thanks for the nice introduction, and hopefully I can live up to the billing. Reliability can be a very serious subject, as you know, when you deal with your customers, right? That's the first thing they're going to ask, well, how long is this device going to work? And in the area of high voltage devices here, which can deliver tremendous amounts of power, like in an airbag deployment in your automobile, maybe the LDMOS device only has to work one time, but you want it to work safely during that deployment. You don't want a partial deployment of an airbag in a crash. So this is what we're going to do, is look at high voltage applications and how you integrate that with 5-volt CMOS. Many times you'll have 80 volts that you want to bring on a 5-volt CMOS chip. Well, the reason it's referred to as a 5-volt CMOS technology is because if you try to operate it at 6 volts, the device is going to operate only for a short period of time. It's going to degrade very rapidly, okay? So the technology challenge is when you bring 80 volts onto a 5-volt CMOS process here, how do you safely drop that voltage before it really gets to the FET? Okay, golly, as the previous speaker, Dave, was saying here, I mean, it looks like the need for analog just continues to escalate. Over in this region here, you've got portable products, which is basically from 1 to 20 volts. You've got automotive printers, 20 to 80 volts. We've got, again, consumer here, because in the U.S. we use 110 voltage power supplies here, automotive. Then you have applications which can exceed 120 volts, okay? In the medical device area, if you have an implantable defibrillator that you use, you have to store 700 volts on a capacitor, okay? You don't want accidental discharges of that when you're driving your automobile and so forth. So the question is, how do you safely handle such high voltages on a 5-volt CMOS process, or maybe even 3.3? Okay, as we're doing this, I'm going to try to make this sound like it's relatively easy. I like Dave's comment to start with. For CEOs, you like to keep things very simple. Well, when you're trying to generate confidence in the customer, you try to keep reliability fairly simple too. If it gets too complex, they think you're trying to disguise something hidden in the process. But these are the basic device limitations that we have, and naturally we don't want to exceed any of these. So silicon tends to avalanche at about 0.5 megavolt per centimeter. Silicon breakdown occurs about 12 megavolts per centimeter. Remember, aluminum and copper, aluminum melts at 660, copper melts at 1083. Now if I put silicon on here, it's at 1410. So generally these high voltage devices, if they start to degrade during high power delivery, which means high temperature, it's usually really the interconnects, the ones that really degrades. It's not the silicon is burning out, but it's usually the interconnects which service that silicon presents the reliability challenge. Metals tend to diffuse at about 2 times 10 to the 7th amps per square centimeter, and of course electrically you always have BVDSS, BVI limitations, latch up and ESD. So once you've solved and make sure that you don't violate any of these fundamental device laws here at time 0, then the question comes, how long will the device live? And generally, kind of a general requirement for semiconductor devices is 10 years at 105. Sometimes the customer will say, well, I want 20 years. Well, but what they really may be asking for is 20 years at 85 degrees C. It can be totally equivalent. So those issues, electromigration, stress migration, TDDB, hot carrier injection, negative bias, temperature instability, power density and dissipation issues, we'll spend quite a bit of time on this since we're talking about high power devices, and single event upsets. They've always been very important for memories, and what I might suggest is that they may also be important for high voltage analog in the future. Okay, so we'll kind of break this presentation in three parts. We'll talk about, okay, how do I make sure that electrically everything looks sound at time zero? Then we'll talk about thermal SOAs. Again, these LDMOS devices, when they're activated, they generate a tremendous amount of power, which means the temperature is going to rise. So how do you safely do that? And how do you model it to get some idea how many times you can safely activate that device during an expected 10-year product lifetime? Then we will look at the reliability SOAs and look at the longer-term issues. Okay, this is kind of the first fundamental device physics property of silicon we'd like to talk about, is always have this in mind whenever you're doing a design, that basically silicon starts to avalanche about 0.5 megavolts per centimeter. Of course, it's a function of the donor accepted density. Now, the reason that's important, because that fundamentally limits the breakdown voltage that you can have for a junction. Now, we were talking about, in fact, the first time I'd worked in CMOS digital for years, then started working in analog, and I had an analog designer that came to me and says, well, Joe, I would like to integrate 80 volts in with a 5-volt CMOS process. And I thought at first it was an oxymoron. You know, how can you do it? You know, again, the reason you call it a 5-volt CMOS is because it degrades rapidly at 6 volts. Well, if you really just, it's kind of basic physics 101, if you look at junction physics, probably the best way of dropping voltage and the safe way is simply drop it across a reverse bias junction. So if you just simply solve Poisson's equation here for these doping levels here, well, you say, yes, you can safely drop 80 volts because the breakdown voltage is 120. So I'm able to drop 80 volts without violating any fundamental device physics associated with silicon. Now, let's pretend that we're process integration engineers, okay? Well, what I will do, if it's a 5-volt CMOS, what I'll try to do is to drop 75 volts, okay, before I get down to the poly edge, okay? Then, as far as operation of the CMOS part, it thinks it's a 5-volt CMOS process here. So we were very easily, by simply using the voltage drop across the junction, we were able to attach 80 volts to a 5-volt CMOS part. And it looks like we were able to do it safely without violating any device physics. And since this is a 5-volt CMOS part, if that's really the voltage at that point, then that device should safely operate for hopefully 10 years. Now, of course, that's just a one-dimensional model that I was looking at. If we look at a two-dimensional profile and actually do more precise simulation, and you can see that it's very close to what we were showing here. In other words, here is VDS. We start dropping the voltage, and by the time that you get down to the gate, it's a rather benign 2 or 3 volts, okay? So I don't expect any damage to the gate. Of course, we have to verify it. And in this region right in here, yes, I am dropping a lot of voltage between the poly, but of course I'm going to make that a thick field oxide. So even though there's a lot of voltage drop, the electric field is still quite low, well below the 12 megavolts per centimeter breakdown strength. So yes, it was not an oxymoron. You can safely drop very high voltages across junction depletions before it gets to the gate, and everything, at least on paper, works out well. Now, let's look at the operation of this device as we hold the gate voltage high and we simply ramp the drain voltage. At some point, we will reach what we call snapback, okay? And the reason that occurs is because you'll start to get impact ionization, and those holes will start to influence the base current from this parasitic bipolar device. And of course, you know, as you start drawing current from it, it's going to be amplified, so you can get in a loop, so you'll get a snapback behavior. So obviously, that's one of the device areas that we have to make sure that, that we don't get in this snapback or breakdown region. Okay, let's just look. Okay, this is what we were talking about here. Normally, at 0 gate voltage, we define this as BVDSS. Then if you have a positive gate voltage here, then you will see a slight weakening of this curve, and usually we refer to this as BVII. But it's quite nice here. You start to, it looks along in this region right here, it looks like a very normal FET. In the higher voltages, you start to develop some kinks. And you can see the kind of current that you're able to draw, a milliamp per micron. And that's per micron width. And of course, you can make these devices as wide as you like. So producing a lot of current is no problem. And in fact, you can see, hey, it's relatively easy. And I say that just relatively easy. Probably the process integration managers here would maybe take some exception to that. But anyway, what I mean relatively easy, you can do it and not violate any fundamental device physics and not violate any fundamental reliability physics also. Okay. So now that we know how to build these high voltage devices in a low voltage CMOS technology that can safely withstand a time zero, so the electrical SOA is good, then the remaining question, will they last 10 years at 105 degrees C? Then the other considerations that we need to look at are the thermal SOAs and the reliability SOAs. Okay, let's spend a little time on the thermal SOAs, because remember, this is a high voltage part, and so we want it to deliver a lot of current, okay? And really, from the device physics, the amount of current that you can deliver is virtually upper-ended, okay? So it's not a problem of being able to deliver the current, it's how much damage is that current going to do to the interconnects which have to draw that, that current, have to handle that current. And generally when these high voltage devices fail, remember the melting temperature of aluminum was only 660 degrees. Silicon doesn't melt till you get to 1410. So it's not the silicon being damaged, it's usually the metallization. Now this was like an electromigration test that you do. Okay, we've got a large number of vias, and in this we actually used pulse waveforms here, trying to replicate really what a real-life device does. Many times electromigration technologists, reliability engineers will use DC currents, but we'd like to use the AC in this experiment to just to verify that the physics doesn't change from DC to AC. We had an average current of about 1 megaamp per square centimeter. That's only about 2x the normal design rule for aluminum, so it's not overly aggressive in the current. The temperature was, rather than 105, it was 179 degrees. Okay? And so you see that the time to fail for that metallization is 400 hours, it's not 10 years. So obviously with elevated current and elevated temperature, or just elevated temperature, you know, the lifetime of the metal can be rather short. Well, how short is the lifetime of the metal? Well, let's start off with an interconnect here. It's designed to last 10 years at 105. If you say, well, Joe, how long will that interconnect last at 450 degrees C? It's going to last about 100 seconds. If you ask me how long it'll last at 550, it'll last about 10 seconds. And of course, as you start to march towards 660, it probably is going to fail the first time that you fire the device here. So this is going to be the ultimate limitation on how much power that you can draw from the device. It's not the inability of the device to deliver the power. Actually, you're going to have to put a limitation on the amount of power density for reliability reasons. So that means that we really need to spend quite a bit of time really understanding what the temperature rise is going to be in the device, okay, as we expect to draw high power from it. Now remember, for the thermal analysis in joule heating, the MOSFET's just a gate control resistor, okay? The only part the gate plays in this is just the voltage to invert the surface. So here's the silicon resistor, okay? So the question is, how much of a temperature drop is required to dissipate that heat? And in steady state, the equation is very simple. It's just the thermal resistance times the power, and we already know the power is just I times V, right? So the thermal resistance, being able to model the thermal resistance, is really the key. Now, if we look, okay, here we have an element of silicon, a differential element of silicon that we're showing here. We have a generation, we have heat generation. So that generation term will continue, and as the heat is generated, the temperature of this element will rise to a point where the temperature gradient can now support a heat loss which exactly matches the input of energy. So it's just the conservation of energy. So this is what I'm saying. When it reaches thermal equilibrium, this term goes away. So it's very easy. Energy in equal to energy out. You don't have to worry about what's being absorbed. So the question is how long it takes to reach thermal equilibrium. That's always considered. And if you work through just look through some of the fundamental thermal conductivity properties, what you find out that essentially you will reach thermal equilibrium in about a microsecond. In other words, this is the thermal time constant, and I went up to about 10 thermal time constants. But you can see really after 2 or 3 thermal time constants, you've essentially reached a thermal equilibrium. So the moral of this story is that if you're doing millisecond pulsing from this power device, you will reach thermal equilibrium. If you get down substantially below a microsecond, then you may not reach the maximum that we're showing here. But most of the devices, if they're operating on the order of a millisecond when you deliver that power, they reach thermal equilibrium. They reach the maximum temperature. Now, you can go through the thermal analysis, and this can get fairly intriguing, and especially if you're looking to full time dependence model. But since we reach thermal equilibrium for millisecond pulses, then basically we can go back and just use a simple thermal resistance model. But you will see in this analysis that where the steepest thermal gradient is in the vertical direction, you lose most of the heat simply in the vertical direction, okay? Yes, a little bit of heat is able to leak out of the sides to the heat sink, but that's what you always keep in mind. Then, of course, if you want to lower that the temperature that this is going to rise, of course, decreasing the silicon thickness is one of the ways of doing it here. And most of the time you go through back grind. After you fabricate the wafer, you go through the back grind to thin it down. And of course, everybody tries to get it as thin as possible, and that'll lower the heat rise, or temperature rise. So anyway, you can go through modeling, and so we'll assume millisecond pulses, and this shows the modeling effort to show the thermal resistance versus area, and if you take the heat generation with a length and a width, it kind of depends on the relative length and widths as we show here, okay? With you know, very high width or length here, obviously you get better heat dissipation from that than you do simply a square. So it gives us some idea of the thermal resistance. Now, knowing the thermal resistance, then that allows me to come in and calculate the temperature rise versus the power. So you can see in this situation right here, for this, if we had a product design with, say, an aspect ratio of 20 to 1, then we could draw, you know, safely draw up to 40 watts from this, okay? Now notice this represents 40 watts over an area. This is 40,000 watts per square centimeter. Now, how many of you, when you were changing a 100-watt light bulb, you touched the glass here and you burn yourself rather severely, right? That's only 2 or 3 watts per square centimeter when you touch it with your finger. So, you know, this is a lot of power, okay? I have seen LDMOS devices fabricated that can produce up to a megawatt per square centimeter. So obviously there's got to be a limitation. The silicon can certainly provide it, but for reliability reasons. And the reason I say reliability, notice I limited things at 350 degrees C, because normally the chip is sitting there with a junction temperature of 105. At least that's what we assume for reliability. So it's already at 105. So if the LDMOS device fires, and it fires such that it's 40 kilowatts per square centimeter, you're going to get a 350 degree rise. And now the metal, the interconnects, is at 450 degrees. And remember how long it's going to last at 450 degrees? About 100 seconds. Okay, so now we've got a limitation here. We understand, you know, how much power can we safely draw from this device. We've got some idea how many times we can fire that device here before we start getting failure. So the remaining issues here are the long-term issues. Well, what about hot carrier? What about bias temperature instability? What about time-dependent dielectric breakdown? Okay, in the digital CMOS world here, hot carriers is fairly simple to characterize, because as you accelerate the electrons from source to drain, what you're going to is get impact ionization. That will change the momentum, change the velocity direction of the electrons. That will create some interface damage here. So you will see the VT degrade, you'll see the drive current degrade for this device. Okay? Now, monitoring the gate injection current is difficult, but it's probably easier just to monitor the whole collection, because that's a majority carrier. So it's very easy to monitor the substrate current in digital CMOS. And you can see, yes, indeed, you start to approach that about a half a megaamp per square centimeter, so you're going to get some impact ionization. So since the substrate current is a good proxy, it's a good proxy for the hot carrier stress, then all you have to do if you're a CMOS digital designer is determine, well, how much substrate current am I really generating? And what you find out that the period of time that you really generate substrate current in a digital operation is a very small part of the total time. So many times you'll hear digital designers and say, okay, if the channel hot carrier lifetime is 1/10 of a year DC, that sounds pretty small, they're totally happy with it, because they know their duty cycle is probably less than 1%. So 1% times 1/10 of a year, you're up at 10 years here. So after you get past that shocking revelation that the DC lifetime is only 1/10 of a year, then you say, oh, actually that's pretty impressive. Now the problem that we have for the DMOS and the LDMOS devices, it's either very difficult or impossible to measure the current due to the layout of these devices. And so you have to take a more empirical approach. As again, the digital CMOS is easy. You only, in theory, have to measure one transistor, and all the other transistors can be modeled by simply using the substrate current. So as I say, life is a little bit easier over in the CMOS digital world. But we really have to take a more empirical approach, since I can't get a hold of the substrate current. And the way we do this here, we fix the drain source voltage, then I'll measure the gate voltage dependence, and it's fairly easy to model. Okay? And we can come over and we can fix the gate voltage, and then we can find the VDS dependence here, and we've got a model for that. So I don't have to take data for every single voltage condition here. In theory, probably I'd only have to take a minimum of 6. Typically we take more than that just to verify that the model works all the way along here. So anyway, from these accelerated, because these are actually stressed to fail, they take some time to generate, then you can model the conditions on. And so you can tell the designer, if you operate in the yellow region, if this region right in here is 1/10 of a year, if you operate in this region right here, it'll last 1 year. So the designer knows exactly what to expect in terms of channel hot carrier performance of the LDMOS device and the drain extended. And usually we'll deliver a nice colored picture to the designer and say, this is it, just keep out of this zone right here. We usually refer to that, either it's a keep out zone or a very, very low duty cycle zone. Okay, now let me move on to TDDB. Okay, like we got a little bit of distortion in that somehow. One of the beauties of silicon dioxide gate dielectrics, especially dielectrics that's greater than 50 angstroms, is that they are really behave very, very nicely. Okay, in fact, if you look at the leakage current through actually the leakage current tends to decrease over a period of time. So the leakage just actually gets slightly better, and so it remains remarkably stable until one day it snaps. Okay, then you end up with a dead short. So you don't have to worry about degradation of the dielectric here as long as it's fairly thick dielectric, greater than 50 angstroms here. You just have to worry about when, at what time, will the dielectric break down. Okay, when you go into the literature, you'll see all of the models. You'll see E models, V models, square root of E models, 1 over E models to describe time-dependent dielectric breakdown. I tend to take a very simplistic view, and I tend to use the E model, okay, because I know it's the most conservative. So I know if it shows good reliability performance using the E model, I don't have to worry about subtle variations. If you take one of the more aggressive models or one of the more optimistic models, then you have to have a ton of data to support your position while you're using the square root of E model, say, versus the E model. So anyway, simple, E model is most conservative. So let's look. Let's take the E model and let's look at dielectrics. And one of the beauty of the E model, regardless what, as long as it's a silica-based dielectric, okay, regardless what you tend to do to it, like in this case you're adding fluorine, these are low-K interconnect dielectrics, OSG, you're adding a ton of carbon, and you just even more hydrogen and carbon down there. But notice that even though the breakdown strength, the slope doesn't change. Well, this is great because that means the wafer fab only has to take breakdown data. Since if you determine this point and you always know the slope, you can determine from your breakdown data, no problem, this material will last 10 years, at least 10 years. And in fact, we took some data at extremely high temperatures just to make absolutely sure that the physics doesn't change at high temperatures and high voltages. We actually went up to 4,000 volts to take this TDDB data, okay? Now, air will break down usually at voltages lower than this. So in order to take this TDDB data, we had to store the units in oil to keep them from breaking down here. So, and anyway, what do we find out? Well, the physics didn't change. So our boss says, golly, did we waste money? Well, no, we just can design at very high voltages and very high temperatures and still maintain confidence. So it wasn't a waste of money. Now, this is essentially the SOA for gate dielectrics because we tell the designer, okay, under normal operating conditions, if you have 100 angstrom gate oxide, an area of 1/10 of a square centimeter, 105, it ought to last 100,000 parallel hours, which is about 10 years. The reference failure rate less than 10 fits. Can operate, you can use a design field of 5 megavolts per centimeter, wobble slope, and acceleration here. And what it is, you can say, well, my chip is much smaller than 1/10 of a square centimeter in gate oxide areas. Well, you can use this to determine how much of additional lifetime that you're going to get. Or if you accidentally have a few transistors that you went greater than 5 megavolts, you can model really what reliability impact they're having. Okay, now let me caution you here. If you're using, say, 65 nanometer technology or maybe even 90 nanometer technology and you're bringing 80 volts on the chip, do not forget about the interconnect dielectrics, okay? At 65 nanometers, that's 650 angstroms. That's where gate oxide was when I entered the industry. Believe me, these interconnect dielectrics are not gate oxide quality. So perhaps you want to increase the spacing when you bring those. Okay, let me talk a little bit about NBTI. NBTI, for years, well, let me back up here. NBTI has existed as long as we've been building CMOS devices. So why in the last 4 or 5 years has it become so visible and so important? Well, when you were building devices with 1 volt VTs, who cared if it shifted to 100 millivolts? That was only a 10% change. Well, today, when you've got VTs at 300 millivolts, a 100 millivolt chip is a 33% change in VT. So the problem has always been there, it's just now that it's reached an acute level. And basically it's related to the breaking of the hydrogen bonds, and the reason that we like to use hydrogen in processing, because it ties up those interface states and makes the time zero value very uniform. It's great for yields, but as you break these hydrogen bonds, you will see a VT change. And again, it's primarily a PMOS issue because the electric field, once you break the bond, the protons will drift in the electric field. If you reverse it in an NMOS, the field actually helps keep the proton in place. And so this shows the VT shifts that you can have here, and it's a very sensitive voltage. And what I'm showing here, even though we really cannot do a lot about this, it's one of those things that you're going to have with CMOS. The good news is that most of the shift occurs within the first year, okay? Well, I can use voltage to accelerate 1 year of lifetime and a few hours of burn-in. So the good news is if you're going to have a problem with NBTI, you will find it during burn-in or certainly during HTOL, okay? Okay, let me talk about one last thing, talk about single event upsets. Generally, this has been treated as a memory issue, but of course, analog is starting to be integrated more and more on system on a chip. So you may have a chip that has a high density of memory as well as analog components. So you need to be aware of this, okay? Basically, the three sources are alpha particles, and they usually are found, they come from uranium and thorium, which is usually found in solder or some of the processing materials you may be using. Then thermal neutrons, and then high energy neutrons here. These are the ones that come from cosmic rays. There's absolutely nothing we can do to prevent those. In other words, every hour, 25 high energy neutrons are striking every square centimeter of your body, okay, every hour. We do it. Now, neutrons are not charged, so most of these just pass right through us without any problem here, don't produce any damage. But if they accidentally hit a silicon atom, in the case of a silicon chip, you'll get a tremendous charge burst in an ionization tract, okay? So in memories, they will certainly cause single bit errors. But what I'm saying is right here, most of the work comes from memories, but in the case of high voltage capacitors, like we were talking about that 700 volt defibrillator, if it produces an ionization tract that shorts the anode and cathode, then suddenly you could maybe have an accidental, deployment of the defibrillator. And if I'm driving down the road, I do not want to see that 700 volts suddenly appear. So I think in analog, it's one of those areas we probably need to look at more closely. Okay, so the conclusion, the business demand for high voltage components is certainly there, no doubt about that. High voltage components such as DEMOS, LDMOS devices can safely be integrated with low voltage CMOS when careful attention is given to ESOAs, electrical SOAs, thermal SOAs, and reliability SOAs. Single event upset is probably something we need to look at a little bit more in detail. As I say, as we start building more system on a chip and then just extremely high voltage components, we maybe need to look at it more closely. Thank you.